Hello, dynamics students. Um, this is our video our video discussing section 17.4 of Hibbler. We're definitely coming into the home stretch here, where we're pulling together all the little bits and pieces to kind of fully describe the motion of um, rigid bodies. This section, we will focus on objects which undergo pure rotations. So you might remember the last section, 17.3, was just had objects undergoing pure translations. Today will be pure rotations. Guess what? Next class, the gloves come off. It'll be full kind of arbitrary motion. So I want to go through the slides for this one. And this is personally, I think this is an easier section, and the example problems they have you do are pretty easy. I want to throw in a derivation. It's actually the same derivation I gave last time, just so you understand where the formulas come from, kind of a full vector analysis, and it makes some of the formulas that the book drops on you kind of just obvious. So, okay, let's get started. So today's objective will be to be able to analyze pure rotational motion of a rigid body, and we'll go through the usual routine. Okay, let's start out with a quiz, reading quiz. When you have a rotational motion, so we're talking about pure rotations, the normal component of acceleration at the body's center of gravity is always 0, tangent to the path, towards the center of rotation, are directed from the center of rotation. Well, if you remember, the normal component of the motion, that's the centripetal part, and it's really actually the positive centripetal part, which means it's going to be pointing towards the center of motion. So the best answer is C. And then, if a rigid body rotates about a point O, the sum of the moments of the external forces acting on the body about point O equals which of the following? Well, it can't be A, because A was the answer when we were summing moments about the center of mass last time. So that can't be right. Let's see. Can't be C, can't be D, because those aren't angular quantities. So the answer is going to be B. We'll explain why in this video. All right, they're giving us a scenario. I think at this point I don't have to kind of show why we're doing this. This is just pulling together all the little facts that we've had so far. We will be studying situations where you have a pin, usually, where something is pinned down and then the object has to rotate about that position. Here's another machine where you take something which is pinned and then you let it swivel down, and you might want to know what's the angular velocity at some point, or what's the angular acceleration at some point, those kinds of quantities. All right. I think what I want to do at this point is go through the general derivation, and then we will simplify it. For the scenario shown in the picture. So I'm going to pull up the whiteboard to do that. All right, so I want to remind you guys, and this is the same derivation I gave last time. So If you understood it then hopefully you'll understand it now. Let's kind of talk about, just kind of remind you where all this comes from. So imagine you've got some point that we want to, and we're going to want to study rotations about that point. It may or may not be a pinned, like a fixed physical axis of rotation, but this is the point we're going to want to study moments about. So I'm going to mark that point here. I'm going to imagine I have some random kind of rigid object, and it's built out of lots of little chunks. All right, and then from each one of these, there is a relative vector. So I'm going to call this point P. I'm going to call this point I, because I'm eventually going to sum over I. And this would be R of I relative to P. So if I wanted to write down the forces acting on chunk I would say, okay, F net on I equals mass times the acceleration of point I. It's a vector equation. And then, since we're wanting to focus on the rotational part, we're going to take a cross product to form the moment of the force. So that'll give me, so I want to take R I relative to P cross F. And if I do that, then I have to take the cross product on both sides, since it's going to be the mass at I times R I relative to P cross the acceleration of point I. And that has the effect of picking out the part of the acceleration which is perpendicular to the radius vector, or picking out the part of the radius vector which is perpendicular to the acceleration. You can think of it however you want. Okay. While this is true, it's actually sort of more convenient to express the acceleration of point I back in terms of the acceleration of a possible point P. So now in this video, since we're going to have pure rotations, the acceleration of point P is going to be 0. But let's just work it out in general, because that'll set us up for next time. So we already know the formula for relative accelerations. We found that the acceleration of point P, oh, sorry, I wrote it differently. We know that the acceleration of point I can be written as the acceleration possibly of a point P. This term will be 0 in all the examples we study today, but for next time it wouldn't be necessarily. And then we have tangential component, which is alpha cross the relative vector from P to I. And then we had minus omega squared. Let's give it, it's going to be the centripetal portion. Okay, this goes back to chapter 16. So if you don't remember where that came from, go back. We derived it in pretty good length there. So this is just like we had a relative velocity formula, we also had a relative acceleration formula. All right, so when you substitute that in, you get mass of I times Ri cross P, oh, not cross P, relative to P, put a parenthesis around that quantity, cross AP. Notice there's no label I on this one, so I'm just going to keep that one separate. And then I'm going to have plus Ri cross, or relative to P, cross the quantity here, alpha cross P. And then when I have to take a cross product of this vector with this term, but that's just going to give 0 because I have R, the relative vector of Ri relative to P crossed with itself. For this one, I'm going to use the vector triple product formula to rewrite this as alpha times Ri P magnitude squared minus so it's back cab is the mnemonic. So you write that as Ri relative to P times alpha dot Ri relative to P. And this is 0 when you're talking about planar motion because the relative vector is in the xy plane. Alpha is always in the z direction. Okay, so let's write down what our final answer is then, what survives. We find that on each chunk, Ri relative to P cross the net force of I equals forgot a factor of mass there. When I multiplied through, I should multiply by through mass here and here. So there's an extra factor of mass right there. Sorry about that. Okay, this was just what we had for one little chunk. We should sum over all the little pieces. And when you do that, all of the internal forces will cancel, and same way with the internal torques, and you only get torques coming from the outside forces. So we get the moment about P equals, now if you think about this, yes, we summed over all, or summing over the positions of all the little bits of mass relative to P, weighted by their mass. So if you divide by the total mass and multiply by the total mass, so do one in a fancy way, this becomes M times the cross product of the center of mass position relative to P crossed the acceleration. So that's just going to be R G P, where G is for the center mass position, cross AP. And when I sum over I, this just gives me plus the moment of inertia relative to P times alpha. All right, so this is my general equation. I've assumed nothing about coordinates and nothing, really. This is just planar motion of a rigid object. That's all I've assumed. All right. Last time, so there's kind of, I guess, some special cases. If P equals G, then I know that the sum of the moments around the center of mass just equals I about the center mass times alpha. Okay, that's easy. Another case, one that's going to be important for today, so this is what we had last time, and then we further said that alpha had to be 0. For today, we want to just not necessarily say that the point P has to be the center mass. Instead, we want to talk about pure rotations, which means the acceleration about point P is 0. And that means, so if P is the pinned point or the pivot point, it's not moving, so it's the acceleration of that point is 0. Set that to 0, and then I can find the moments about that point. Okay. So in fact, hopefully this looks familiar. Hopefully these both do, actually, but this is, in fact, both of these, I should say, are just what we did in physics 1. Okay, this is exactly what these are the exact equations we worked out in physics 1. We picked a point, P. We only study pure rotations in that case. Did we do that? I take it back. We did have a few rolling problems, but anyway, we didn't do a full. We didn't pick arbitrary points, so we didn't write the equations in the kind of full version. We used one of these two. Notice, even if the object is undergoing some crazy motion, if you study the moments about the center mass, this top line is still true, regardless of what the acceleration might be. To use this, you're really talking about pure rotations. Okay. So that's the key equation we're going to use today in our examples. What the book or what the lecture slides do is they further specify and choose coordinates. So let me write down our full equations now. When the acceleration at point P is 0. Okay, so it's like imagine I've got some shape and I'm going to have a point that's pinned down and the shape's going to rotate around it. Let's say the center mass is over here. Then what we're going to have is first of all, if you follow the motion of the center mass, it's going to trace out a circular arc. So we know immediately that the acceleration the acceleration of the center mass tangent to the arc, well, that's going to look just like circular motion. The tangent component is going to be r of the center mass relative to the point P times alpha. This is for the scalar components. And similarly, the acceleration normal that's simply going to be the centripetal term. That's going to be rg relative to P times omega squared. Okay, because the center of the object undergoes a pure rotation. So you have these terms. So we would write down Newton's laws, and you would say F net in the tangent direction must add up to Rg relative to P times alpha. We'd say F net in the normal direction is going to be Rg relative to P times omega squared. And then we come to our result from over here. The sum of the moments about P equals the moment of inertia about P times alpha. Okay, so these are the equations we will use to solve problems. Let's see how the book writes it. It's really the same equation. Okay, they're calling the point O, but okay, here's a pinned point. Here's the center of mass. They identify a tangent and normal direction. What's the formula? So you say sum all the forces in the normal direction. That's supposed to give you the acceleration of the center of mass, and we were talking about the normal direction. So you're just going to get the centripetal acceleration. And I think I may have forgot the factor of mass there, so just watch that in your, just watch that factor of mass when you write it, pull it all together. Should be mass times acceleration. The tangent direction, you only get the r alpha term, and then we have our torque equation. Now, they wrote the torque equation about the center of mass. That's fine. That's always true about the center of mass, whether it's rotating or undergoing general motion. That's fine. We also can use, well, they call it the parallel axis theorem. It's really no different than the derivation we gave a moment ago. And you end up with the moments not about the center of mass, but about the pinned point, the point that's that has no acceleration. Okay, so these are the equations I just wrote down on the whiteboard or in the whiteboard space. How will we solve these problems? Well, okay, got to choose coordinates. You want to identify the tangent and normal directions followed by the center of mass. Draw good free body diagrams, accounting for all the external forces. The internal forces don't matter, they cancel. And then you might need to draw a picture for the inertia forces and couple. I think they're just talking about that they're called kinetic forces. And then you want to compute the moments of inertia about whatever axis is appropriate. And then write the three equations of motion. You're going to have two from the force law and one from the rotation torque law. And if there are more unknowns than that, there has to be some little wrinkle in the problem that allows you to solve it. In this case, it's going to be things like rolls without slipping, allows you to relate various quantities. All right, so we come to our first example. Pretty simple. This is something we can and probably did do in Physics 1. So we have a pinned point, and we have a rod that extends out 3 meters from the wall. They tell us that there is a moment applied at the pinned point, excuse me, and we're told that it is currently moving with this angular velocity. The task is to find the angular acceleration, alpha, and the reaction at pin O. So they want us to find the forces generated at point O when the rod is in the horizontal position. And just a warning, well, watch your minus signs as always when things rotate. They're going to call the tangent direction positives. They're going to say that clockwise is positive, whereas I would feel better saying that counterclockwise is positive. So you just have to watch your minus signs. Okay, so our plan is to kind of choose coordinates, come up with a free body diagram, write down F equals ma in both directions, allowing for the possibility that there is some sort of a force generated at the pinned location, and then write down the torque equation. And you could do the torque, write down the torque equation about any point, but the easiest one is going to be to add up the torques or add up the moments about point O. And that allows us to ignore the details of the normal forces applied here. All right, so that's going to be our method. Switch over. I'll solve it. Yeah, Sorry, from what I was saying before, I forgot the factor of mass there. So this seems to be a problem for me today. Okay, so we're going to go through example 1 here. You know what I'm going to do? I'm actually going to go back. I'm going to do this inside the PowerPoint program. Okay, so we're going to exit this. Um, and I'm going to insert sorry, struggling with getting the right window visible. There we go. Struggling with that. I want to insert a slide. All right, so this is going to be example 1, and kind of draw a picture and run through some numbers. So I have a wall with a pinpoint, and there's a rod extending out. And we are told the following things. We're told the length is 3 meters. And we are told there's a moment. I'm going to say that is, the problem said it was 60 Newton meters. I'm going to say it's negative 60 Newton meters because it's clockwise. And we are told that the angular velocity, omega, is 5 radians per second. And I'm going to say that that's negative 5 radians per second. That way I'm in full control of my minus signs. We are also told that the mass of the rod is 20 kilograms. So let's draw a good free body diagram here. So I'm going to mark the pinned point, and I have my rod, and I don't know what kind of force is generated at the pin. So I'm just going to draw some random arrow. I'm just going to call it some sort of a normal force. And this is being applied at point O. The book likes to call this force the force O, which is applied at position O, but I'm going to just call the force a normal force. It points in some random unknown direction, and I'm going to say it's applied at point O. And then we have the weight, which is applied at the center. So we have acting down, we have a weight. Okay, so that's going to be my free body diagram. I've identified the forces. Oh, and then I also have the moment, which doesn't contribute to the force equations, but it does contribute to the torque equation. All right, let's just grind it out. Oh, one other thing I want to say. This point at the center of mass follows a circular path. So this point follows a circular path. And therefore, I know the radial component is going to be the acceleration radials, or I guess we're calling it the normal direction, is going to be the centripetal piece, which is going to be the radius times omega squared. I know omega. The radius is just the distance from the pivot to the center of mass. And then the tangential piece is going to be r times alpha. Now, I'm going to want to call alpha negative, and so I'm actually going to get a negative tangential component for acceleration, and that's okay. And similarly, I would prefer to call towards the center of rotation the negative radial direction, but the book and the notes work with they put an extra minus sign in there. So anyway, they'll have a positive quantity there. All right. So I'm going to go ahead and say then that this force has two pieces. This normal force has a normal force in the y direction, it has a normal force in the x direction. And what I'm going to see is that the direction of the normal force here, as I drew it, it needs to point away from the wall, whereas when writing the formula for the acceleration, it is actually going to point towards the wall, so there's a relative minus sign in that. So what I'm going to do is I'm going to write down the net force in the normal direction. That means towards the center, calling positive direction towards the center of the circle. That's going to be minus the normal force in the x direction, because that points away from the center of the circle. And that's it. And so that has to equal m times, well, the radius for the weight would be the length over 2. Not for the weight. Right, not it's for the weight, but for the center of mass, because the force equation follows the motion of the center of mass. So the radius you'd use is L over 2 times omega squared. For the net force tangent, that is going to give me, well, I have minus mg, so weight's going down. I have plus the y component of n. I don't know if it's actually positive, but we'll let algebra determine that. And then I have, okay, and that's it. And that must equal the mass times acceleration of the center of mass. Okay. So, all right, we have these equations. Incidentally, we know the length is 3. We know omega is 5. We know the mass is 20. You can immediately write down that the normal component, that the normal component in x equals 750 newtons, because you know all the numbers. We can't solve for the y component because we don't know alpha yet. So we need another equation that's going to come from the torque equation. All right, the torque equation. The torque equation, or the moment equation, and we have to choose a point to study moments about. We're going to choose it to be the pinned point at where the rod joins the wall. So I'm going to say the moment about point O equals, well, first of all, you have the moment, the external moment that was being applied, which was a minus 60 Newton meters. And then you have the moment from the weight of the rod. Well, that's going to cause a clockwise rotation. So that's minus L over 2 times mg. And that's it. Those are the two moments. You have the explicit moment, the external moment, and then you have the moment from the weight. And that must equal the moment of inertia about 0.0 times alpha. Looking at the shape of this, we see that this is just a rod rotating about its end. So I know that I, 0.0, is 1 over 3 m times L squared. We know that because of 2 videos ago where we calculate moments of inertia for a rod. Very good. So we can try to, we know that everything on the left-hand side, we can solve for alpha. And then once we know alpha, we can back substitute and find the y component of that force generated at the pin. Plugging in my numbers, I get minus 60 minus 1 and sorry, 3 halves, so it's 1.5, times the mass, which was 20, times g, which is 9.81. That has to equal the moment of inertia, which is 1/3 mL squared times alpha. Let's plug in our actual values here. The mass was 20 and L was 3, so L squared is going to be 9 times alpha. So when you solve for alpha from this, you find negative 5.9, and it'll come out as radians per second squared. Now, once you have this number, we can back substitute into here and solve for the normal force in the y direction. And when you do that, you simply get 19.2 newtons. Let's compare that with the book's answers. They pretty much do the same thing. They just label things a little differently. They maybe handle some minus signs a little differently, but in the end, it comes out the same. They get the force generated at the pin tangent, that would be the y component. They get to be 19, and I found 19.2. And they find alpha to be 5.9. That's exactly what I had as well. As far as the x direction, so that would be the O with the subscript of normal in, that's actually up here, 750. That's exactly the same number that we found. So their analysis is a little different in the way they do it, but it amounts to the same thing. Let's do another example. This is a problem where there's sort of a pivot. You have a beam or rod, which is off center. And originally there would be a rope holding this and it snaps. So what can we assume? Well, we can assume that initially the velocity of everything was 0. It was all starting from rest. And the problem also tells us about the mass of the rod, and it gives us various geometric quantities. So we'll work through that to get our answer. The goal is going to be to find the reaction forces generated at the pin and the angular acceleration of the rod just after the cord is cut. So when you cut it, what is alpha? Sorry, I lost my, there we go. All right, so I have the following picture. There's a string attached to this beam. The center of the beam is here. The pivot is here. We are told that this distance to the pivot is 0.6 and that this distance is 0.9, sorry, 0.3. Sorry. Which would mean that the total distance is 0.9, which means the distance to the center is 4.5. Phew. So, kind of clean this up here. So what we know is that the distance to the center of mass is 4.5 from the end of the rod. And since this is 0.3, this must be 0.15 is the distance from the pivot to the center of mass. Okay. So first step is going to be to choose coordinates. We're going to use tangent and normal, which in this case align with x and y. And then we want to develop a good free body diagram and basically solve it using Newton's laws. So a free body diagram is, well, okay, so here I've got this rod. I have a normal force. The normal force is up. I know the normal force is straight up because originally the wire was hanging straight down. So that means in that first, there must have been no, and it wouldn't have been able to support any horizontal forces. It would have had some angle to it. So if that's the case, the normal force must be straight up. So that's that point. I have the weight, which acts as if it was concentrated at the center of mass. And those are really the only relevant forces. So next up, let's write down, well, okay. We know that the center of mass follows around a circular arc. And in particular, we know that the acceleration tangent must equal the radius from the center of mass to the pivot times alpha. Just for fun, we also know that the acceleration normal would be the radius from the center mass to the pivot times omega squared, which is 0, which is another way to conclude that there can't be any force in the x direction. All right, so then I write down F net in the tangent direction because we've already handled because we've already handled the normal direction. That must equal, well, we have a normal force applied at O plus the weight, which is going to be minus mg. All right. And we know, well, okay. And we know that that must equal R times alpha. Let's just check our minus signs here to make sure I've got it right. So if we go back to the picture, I know that if you cut that wire, it's going to rotate counterclockwise, which would be a positive alpha, but that should correspond to a negative acceleration. of the center of mass. So we will have a positive alpha well, that'll be a check for us to make sure that we get it all right. And then we can work out the moment equation, which is the moment about point O. Well, the normal force doesn't generate a moment about point O, but the weight does. So that's going to simply be, and it's going to be a positive moment because it is clockwise or counterclockwise. So it's going to be mg times the vector from the pivot, or sorry, we're calling this point O. Should have kept that as point O to G. And that's supposed to equal the moment of inertia at point O times alpha. So these are our two dynamical equations of motion. What we need to do is find the moment of inertia, substitute in there, find alpha, and once we know alpha, we can get the normal force. Okay, that's our roadmap. Let's do it. So to find the moment of inertia, I would say I'm going to use a parallel axis theorem. I'm going to say the moment of inertia about point O is going to be the moment of inertia about the center of mass plus the amount that we shifted it, which I'm calling R G relative to O squared times M. And so when I have a rod rotated about its center, that's 1/12 ml squared plus Rg relative to O times the mass. And if I have that formula, I can go look on the previous page, put that into here, and solve for alpha. So I guess working it out symbolically, I have alpha equals mgr divided by 12th. And plugging all my numbers in, I get 16.4 radians per second squared. Okay, so that's found I, and then I substituted in, found alpha, and then the last thing I wanted to do was to substitute into the tangential force equation to get the normal force in the O direction. When I do that, I get the acceleration. Well, okay, so I immediately know the acceleration in the normal direction is going, sorry, not normal direction, tangential acceleration, which is R times alpha. And that is 2.45 meters per second. Okay, and then from from the tangential equation, I get that the normal force y minus mg equals mass times acceleration tangent. And I need to put a minus sign in here because I want to say down is negative, whereas the book or the PowerPoint, as we'll see, basically reverses the signs on everything. And basically plugging in the numbers, I get 110.4 newtons when you plug everything in. Let's compare that to what the book finds. It's kind of a similar, same basic plan, right? They all have the same basic equations. There's really no trick to it. They get the same alpha, and I had 110.4, so that's within a rounding error. So it works out. All right, so those are the two examples I'm going to do in this video. And then in class, I'm going to ask you this concept quiz, so I want you to think about it. You have a rigid bar of some length. It's released from rest in the horizontal position when the angle is 0. Okay, so that means the rod is flat against the ceiling. And it asks when the angular acceleration is maximized. And then also, it asks when the angle is 90 degrees, what is the horizontal reaction, horizontal component of the reaction at pin O. All right, so I'll start class with those next time. If you want, I'll go ahead and show you the group problem we're going to start with. Is really, we start with I don't know, some sort of a weird springboard, which is in equilibrium, and then an extra 100 Newton force is added, and we want to find what is alpha. So that's going to be the first group problem we do. Okay, I'll talk to you guys tomorrow. Bye.